All right, so then let's get started. Today is the 19th installment of our lecture on image processing, retrieval and analysis. And what we are going to do today actually is very much in the area of image analysis. I have mentioned it earlier, we will look into rather classical ideas in the area of image analysis. Some of them may indeed appear almost trivial. Nevertheless, they have their merits. They are of practical value, and I have to, inform you about these ideas of connected component analysis, probably the Chamfer distance, and in particular the Huff transform. But before we will dive into that, let us also briefly remind ourselves as to the topic of the last lecture. The problem we looked into there was the problem of region segmentation, and today I actually brought you an example as to what that may mean in practice. Here is an image, and we as intelligent, cognitive human beings are of course really easily capable of recognizing that this image is composed of distinct homogeneous regions, which are homogeneous not in the sense that they sort of have exactly the same color at every pixel, but they are homogeneous in the sense so that their texture is comparable from pixel to pixel. Look at the roof here. There is some tiling on the roof, and that of course causes some pixels to be brighter, some pixels to be darker, but the texture of what we would call the roof is a different texture of what we would call the sky, and that is again a different texture of what we would call, I don't know, the facade of this building. And we may then try to come up with a measure of how textured a certain tiny neighborhood in such an image is. What is sort of the characteristic texture around here, around here, around here, around there, and so on and so forth. We may compute texture measures for every pixel, and after that group pixels which have more or less similar features into larger coherent regions, and this is what we get in this example. So please note that this example is a rather trivial one, and even though it is so trivial, the result almost looks disappointing. Right? This, I don't know, people would have probably segmented it differently. But it's not that bad either. So how did I do this? Let us remember that we defined a region to be a homogeneous area in an image F. And this notion of what is it to be homogeneous was tied to the idea that there is some sort of a predicate, let's call it P, which we may evaluate on all of the pixels in an image. And in particular, if two pixels belong to the same region, then we would say that they both meet that particular predicate, and a region would then be a collection of adjacent pixels, neighboring pixels, all meeting that predicate. And if we were to extend the region by another pixel not yet assigned to that region because it did not fulfill that predicate, if we thus were to extend that region by that pixel, it wouldn't be a homogeneous region anymore. Of course we can, determine arbitrary sets of connected pixels and would call it a region, but we want these connected sets of pixels also to have the same properties. Yeah, formally we would say that an image F is a union of lots of regions, Ri. We would, in this sense, does not have to be the case, but for what we discussed, it was one of our prerequisites, require these regions to be disjoint. So if we look at the intersection of any two regions, it should be empty. Again, in general, that does not have to be the case. We can do some sort of fuzzy or fuzzy region segmentation. But here we actually went for crisp regions. We want these regions to be topologically connected. That is, every pixel within that region touches at least another pixel in that region. So a region has to be some topologically connected structure in the sense that every pixel is adjacent to every other pixel or any other pixel in that region. If there is some patch here and some patch there, we'll call that two regions because they are not connected. We want every region to meet the same predicate. And again, if we evaluate the predicate for, this actually should have been a union and not an intersection, I'm sorry. It should be a union rather than an intersection, so turn it upside down. If we were to evaluate the predicate on the merger of two regions, it should evaluate to false. Evaluating this predicate, whatever it is of course tantamount from the point of view of pattern recognition or data analysis to a clustering problem. And what is being clustered here are texture features. And that of course raises the question, what are texture features? And there are many texture features. The SIFT descriptor we studied earlier was not introduced as a texture feature, but it could of course be understood as a texture. We could actually compute the SIFT feature vector at every pixel in an image, not just at certain key points, and then use these SIFT feature vectors to cluster pixels into coherent regions. There are others, famous histograms of oriented gradients. What else? There's so many I can't even remember all their names now, but what they all have in common is that in order to be a texture feature, they have to be computed from more than a single pixel. That is to say, all these texture features are considered at a pixel and are determined from a neighborhood about that pixel. So they are computed from a collection of pixels being adjacent to the pixel currently under analysis. And the particular example we looked into as sort of the canonical texture feature, if you want to, is the idea of gray level co-occurrence matrices, or GLCMs as people like to call them. They are defined like that. If the image has L gray values, typically ranging from 0 to 255, this matrix would be a 265 by 265 matrix, and mu would indicate gray value levels or gray levels. And looking at the way I have defined it here is to say that we are filling such a matrix with co-occurrence counts. What we can see here is we would set the entry of this matrix. It depends on two parameters, d and alpha, I'll talk about in a second. We'll set the entry to the number of pixels in that neighborhood for which one of the pixels in the neighborhood, say Fij, has a value of mu, and then we look at a certain displacement from the pixel Fij, and if that one has a value of mu or an intensity of mu, we would increase the entry of this gray value occurrence matrix by 1. So this counts how often do we observe a pixel with an intensity of mu and a pixel with an intensity of mu in a certain spatial relation to each other. Right? Here I express this spatial relation in terms of deltas, delta x and delta y, but last time we actually talked about distance and angle, so the distance between one pixel and another and the angle between these two pixels, typically chosen as the parameters of these gray value co-occurrence matrices. Here I have expressed the distance and angle in terms of a displacement vector, but that is of course equivalent, right? What we typically do in practice is that, okay, so these matrices have to be computed for every pixel. It's a nightmare in terms of computational efficiency. This is anything but computational efficient, right? But it works. It gives good results. So here, sort of performance is sacrificed in terms of like runtime performance is sacrificed for accuracy or performance in I don't know, segmentation. And even though it is very, we have to be careful, expensive, I should say, expensive to compute just one such matrix for every pixel in the image, what we typically do is we actually compute several such matrices for every pixel. And these several matrices are computed with different choices of d and alpha. Quite typically when I say, I don't know, the distance between two pixels is supposed to be 2, and alpha is 0 degree, 45 degrees, and 90 degrees. So that would be 3 choices, but there might be actually more. Don't ask me like how to choose that. Again, there's no answer to that. There really is not, right? And I already said it, these matrices are square and of the dimension of the number of different gray values in the image. And of course this would work with color as well, but for the sake of simplicity, once again, let's focus on intensity images. Now once we have one such matrix, can of course try to do classification with the matrix itself, but that is a collection of 256 by 256 numbers, you know, and if we were to further process these numbers, we could, for instance, do discriminant analysis with that. We study how to do that, right? But maybe we can sort of simplify our lives by turning these 256 square numbers into just a single number, compute the statistics from this large collection of count variables, and we looked into the idea of energy contrast and homogeneity. Right? I'm not actually repeating them here. It's not really worth it. You know, you have seen this, and if you ever are to use these things in practice, which may happen, then at least you know where this comes from. And by the same token, now that we have a feature attached to every pixel, we can go into the clustering problem. And of course we can use, we can look at this from the point of pattern recognition and machine learning, use some of the clustering algorithms developed in these, for instance, k-means, just as sort of the most famous one. But with respect to image analysis, there's always this specific fact that we can think of a digital image, we typically think of it as a discrete function, right, assigning intensities to certain discrete coordinates, but we can also think of it as a lattice graph, right? And by a lattice graph, I mean a graph structure, something that consists of nodes and edges. And by sort of my gesturing, you can already see that these graphs here, of course, are grid graphs. Right? The pixel can be, and this is another interpretation of what an image is a grid graph, where the nodes carry certain intensity values, and adjacent nodes are connected, at least conceptually, by an edge. And this is something that is not generally given in machine learning and pattern recognition, but it is given for image analysis. So therefore, actually, when it comes to image analysis, we may think of specific clustering algorithms, something you would never do in pattern recognition and machine learning in general, but something that is rather efficient or easily implemented with respect to these grid graphs, with respect to the images we are interested in. And we looked at a couple of them, and we might have looked into that in more detail, but to be honest, it's not worth it. It's not worth it. You know that they exist, and you now know what that means. Now, let's move on to something new. The headline here is two-pass algorithms. That is to say that we are now studying something which, like a couple of things, which are specific instances of a more general way of computing with images. The first problem we are looking into is the problem of answering the question, how many regions are there in an image? Right? And let me go back to the house here. Say we have been able to cluster the image into coherent regions, and now every pixel is carrying a certain number, right? And if we plot the image or write it to disk, using these numbers as intensity values, we get this. But still, how is the computer to know that, I don't know, this is something else than this? The number is the same, because the feature we computed for this window is sort of the same as we computed for this window. The texture is the same, but these two regions are topologically disconnected. They are not immediately adjacent to each other. But the number contained in that image for pixels in each is the same. So how is the computer to know that they are still different regions? This is the question we're studying now. And of course, we can answer that. We can actually answer the question, so if we can distinguish pixels in different regions, then we can count the number of regions, right? And without further ado, here is how we do this. And this is actually the idea of connected component analysis. Note that on the right there is a binary image, right? And also note that in order for this example to work, it does not have to be binary. This could all be pixels with a value of 3, and this could have, I don't know, pixels with value of 15. Here I assume that all these black pixels have a value of 1 and the white values in the background have a value of 0. So this is a binary image, but it doesn't have to be binary, okay? For us, it's easy to see that there are two distinct regions in that image. And the question is, how can we determine that automatically? And this is often approached with something called connected component analysis. It very much sounds like a matrix factorization approach. It has nothing to do whatsoever with matrices. Like seriously, not at all. And still it's called connected component analysis. So the fundamental ingredient here is that we assume that there is a mask. And we would superimpose this mask on this pixel. So this one here, this empty entry in this mask, always corresponds to the pixel we are examining. And therefore these other three entries are sort of the pixel on the top left to the pixel we are examining, right? Now here's how this goes. We iterate over the image in a first pass, two-pass algorithm, from the upper left, row-wise, to the lower right. And check if the pixel we are currently examining is a foreground pixel. In our case, the foreground pixels are black. So if this is the case, and the pixels to the upper left have no neighbor in M, which is to say, well, are background pixels. So if all the pixels to the upper left are background pixels, then what we do is, in the region image to be created, we assign a new label to this pixel. Let me do this. So instead of 1, 2, and 3, I'm using colors here, okay? So this is the label for this pixel. We move to the next one, and this is a background pixel, so nothing for us to do. We move to the next one and check the 3 pixels to the upper left and find them all to be background pixels. So what happens? We will assign a new label to that pixel. Here we go, a new label, right? Then we move 1 pixel to the right, nothing happens, it's a background pixel, and we move another pixel to the right, new label. Right? All these 3 pixels in this row here have been assigned new labels. Then we continue in the next row. Now we are here, and we examine the pixels in this mask, and we find, well, 2 of them are background. I actually, I could have been more precise here. 2 of them are background, we don't count those, but 1 of them has a label already. So in a sense, we look for the smallest label in this neighborhood defined by the mask. I should have been more precise here. The smallest label in that neighborhood is, of course, sort of the orange one, like label 1. And then it says register equivalent labels. Let's see what that means in a second. But before we look into that, let's move on to the next pixel. What kind of a label will it get? Orange. Let's see. Yep, very good. Now, next pixel. What label will it get? Orange. Aha. Funny, right? Because here we had a choice between two labels. But the orange one is sort of the smaller one, the one that came first. Let's call orange 1, green 2, and purple 3, right? So here we would have looked into the neighborhood and found that there are two labels for us to choose from, and we choose the smaller one. And now this matters, right? Because working on this pixel, we realize that the label 2 and the label 1 are actually equivalent, right? Because the regions we have labeled so far in this image now become connected at this pixel. And that is to say there is a topological connection between this and this one. And so therefore, we couldn't know this when we were here. Right? Now we know that. But that tells us that label 1 and 2 should actually be the same. And we register that in some appropriate data structure, say some dictionary. Right? We register the equivalence relation. We continue, nothing will happen. What will happen with this pixel? Purple, let's see. Yeah. Okay, now, without further ado, next row, orange, orange, purple. There we go. Right? So, this is the situation after we have passed from the upper left to the bottom right. And we have this issue here. So therefore, in this algorithm, we carry out a next pass, actually again from the upper left to the lower right. Can do it from lower right to upper left, but here it really doesn't matter. What we do here is, in this second pass, we again go over all the pixels and relabel them. So here we would look for the label value with the lowest equivalent label, but for our case, label 1, the lowest equivalent one is 1. Here nothing happens, is a background pixel. What happens here? Exactly. Yeah, it will now become orange. Let's see. Yes, it does. Because examining this label, which was 2, with respect to sort of the equivalences we have stored somewhere, we now realize that everything that is labeled 2 should probably be labeled 1. And so we do this here. Right? And then nothing happens. What happens here? Purple. Nothing happens. Purple, we are done. Right, so actually, I don't have to continue passing on it, but this is how we uncover. Like once we are done with these two passes over this image, we know there's actually two regions here. Right? Because now every pixel in here has a label of 1, and every pixel in here has a label of 3. And that is something that the computer can distinguish. Right? Even though sort of the features in the original image are exactly the same for these pixels, now we know that there are two disjoint regions. That was connected component analysis. Here is an example, a binary image, this time consisting of two regions. After the first pass, this algorithm has, you cannot see this, but there's actually lots of shades of red here, has found 81 different regions. Right? This is because this pixel here, say, has a different label than all the pixels that have been analyzed so far. There's like nothing on the top left to it. The same would go for this one. So there's like lots of regions or parts in this image where the top left check in the first pass would say, oh, there's nothing there, so let's assign a new label. These actually are 81 shades of red. Right? And then after the second pass, we get this is just two regions. And this is, of course, from the point of view of computational efficiency, trivial. Well, this, you can't get that any faster. That is really, it's very nice. So by means of two passes over the image, we can identify disjoint regions. Here is how I did that in Python. I first read an image called cat. and it is represented as a PNG image that is on disk. These pixels here are represented as black values and the background white values, so 0 and 255. This is not the representation we like when we talk about binary images, because when we talk about binary images, I want these ones to be called 1 and these ones to be called 0. So therefore I have this conversion here. I read the image, divide everything by 255, which has the effect that the white pixels will now have a value of 1 and the black pixels will still have a value of 0, because 0 by 255 is 0. And then I subtract 1 minus this, and that sort of inverts it, and this is now a true binary image in the sense we always talk about. And then I was struggling with myself, because the algorithm we just discussed is easy to implement, but this equivalence store is somewhat of a tedious data structure, even if you use Python dictionaries. And I actually have written it out, but I know. There is a module called SciPy-AnyImage, and this has a submodule called measurements, and this has a submodule function called label. And that is exactly what we just discussed. So what we just discussed in Python, if you do it right, boils down to just one line of code. Okay, next one. Let's look into yet another two-pass algorithm. This one's called the Chamfer distance transform. The idea is called the Chamfer distance transform. Let's say we're given a binary image, so something consisting of pixels with values 0 and 1. And again, let us, I don't know, for the time being, assume that 1 indicates foreground pixels and 0 background pixels. We might actually be interested in the question, how far is a certain foreground pixel from the closest background pixel? Why that may be interesting, let's discuss later, but that is our problem here. How far is a pixel away from the background? Here is such an image. I'm using white to indicate the background and black is the foreground, so this is 1, this is 0. And here is the chamfer transformed image. And this is just for reasons of visualization that it looks like a gray value image. But see this skeletal sort of structure here? A pixel here is very far away from the closest background pixel, whereas a pixel here is very close to the background. And the intensity shown in gray here, the darker, the farther away, actually indicates how far away a pixel is from the background. Can you follow me? All right, it's easy, right? This is what we want to get. With respect to binary, it's like interesting if you're into shape analysis, but the reason why people actually use this is typically the other way around. You have an image, you compute an edge map using, I don't know, some gradient operator, Sobel or whatever. You extract edges from that image. Now I have, again, colored them such that the edges are sort of black and the non-edge pixels are white. And mentally we now understand black to be the background, the lines to be sort of the background structure of the image, and everything that is white to be foreground structure, something that has nothing to do with edges. Here is the resulting chamfer distance. I know that you can't see anything. I can actually see something on my screen, but even on the screen, it really does not look so clear cut as in the example with the cat. Now, so apparently it is interesting for people to turn images like this into images like that. This is the chamfer transform. Why would that probably be? Because we cannot really see that here, but we can do template matching in these images, right? Imagine you would want to detect an image or part of an image that has a certain, say, linear structure. For instance, a traffic sign, right? They often are triangular or rectangular or octagonal or circular, whatever, but they have sort of clear-cut edges and typically stand out from the background. You find them in. I should have brought an example with a traffic sign. Next time I teach this course, I'll bring a traffic sign example. And your task would be to identify traffic signs. And if we were to do this with the template on the original image, we would have to suffer from the fact that, well, there might be occlusions, there might be variations in the background, variations in the intensity, lots of variations that are really difficult to attack using templates. But in any case, it is very likely that we can compute an edge map. Right? So we could do template matching on the edge map. But then we would still have to suffer with ambiguities as to scale. We would have a template on a certain scale, and maybe it would not match perfectly here, but be slightly too big or slightly too large. But if we were to express these edge maps in terms of distances to edges, then we are finally dealing with a representation in which, you know, even if our template is slightly too small or slightly too large, it will give a better match at certain places in the image than at other places. Right?
Distance will be a boundary distance, right?
You know, here we have numbers between 0 and something,
yeah,
right? And for the template, we would do the same. So you have a clear-cut picture of some traffic sign. You compute, for this small picture, you compute the chamfer transform. And then you just slide this over here. And it is robust against variations in size and slide rotation and stuff like that. It's more robust than if we were to do it here. Right? This is it. This is why this is interesting. And to compute this can be done very fast. We'll see in a second. Right? So this is another sort of ingenious approach to image analysis that required a lot of human, again, ingenuity, and it works really well. This is a very fast way of matching templates where the objects you are interested in are very much characterized by certain linear structures, or at least clear-cut edges, or can be circular, right? If there's a strong edge in the object, or edges in the object you want to locate in an image, then this is probably a good idea. So how is this done? I have brought you another binary image. This is really not an interesting binary image, but it's a binary image nevertheless. And again, we will approach this problem of computing the distance to the closest background pixel by a two-pass algorithm. And it involves two parameters, A and B, and A will be set to square root of 2, and B will be set to 1. And now what we do is we iterate from the upper left to the lower right. If the pixel we are currently examining is a foreground pixel, as this one, we compute the corresponding value for the distance image, which has been initialized to 0. I have not made this explicit here, but it has been initialized to 0. Again, according to the three neighbors to the upper left. Right? So we have x minus 1, y minus 1. I'm using the mathematical notation here, but for matrices you get this. So x minus 1, y minus 1, x, y minus 1, and x minus 1, y. Right? These three pixels are being considered here. We look at their values in the distance map computed so far, which at this point should be 0 as they are background pixels. I have initialized that to 0. And to this one, we add a value of a, which is square root of 2. Does that make sense to you? Square root of 2?
Yes.
Yeah, it's the distance between here and there, right? And to the value here, we add b, 1. It's the distance from here to here. And here we add 1 again. So this is the reason for choosing a and b. And again, I was too lazy to put a square root of 2 every time I write this. So let's go for it. What would be the minimum here?
This one or
yeah,
this
well,
one?
it doesn't matter, right? Is 1,
Yeah.
right? Because either one is like minimum here, actually like all of them are 0, but one is 0 plus a is square root of 2, 1, 1, minimum is 1. So let's go for that. Let's choose 1. There we go, this time I'm labeling them like this. Let's continue. Next one will be a value of 1. Yeah, next one will have a value of, where does it come from, the 1? From here, right?
Yeah.
Because we have 3 values here. This one is 0, 0, 1. 1 has to be added by 1. So this is actually, from examining this one, it carries a value of 2. This one has a value of square root of 2. This one has a value of 1. So we go for the 1. There we go. So next row. This is the 1. And now?
Now square root of 2.
Square root of 2?
No, sorry. 2.
2, yeah. 2. Because if we examine this one, there is a 1 plus 1 is 2. 1 plus square root of 2 is 1 plus square root of 2. And here is 1 plus 1 is 2. The minimum is 2. Same here. And this one, the next one will have a value of 1. All right. Now comes the interesting row. What about the first pixel? 1. Good.
The next one will be square root of 2.
Yeah, again it's 2
No,
because
sorry,
yeah, it's 2, and this 2 comes from here, right? Because we have 1 plus 1, 1 plus square root of 2, 2 plus 1. So it's actually the minimum is 2. And now comes a crazy one. 3. Exactly, right? And the next one will have a value of 2. Great. Okay. That was our first pass over this image. And this is of course horrible, right? Because the distance from this pixel to the background is anything but 3. But we couldn't know from passing through this. And so therefore, we have a second pass. This time we pass from here, lower right to upper left. And this time is actually, like for this argument, it's important that we start here. For the connected component, we could have also done it, but it doesn't matter. Here it is important that we start at the lower right. And we sort of, where we looked at the pixels to the upper left in the first pass, we now look to the pixels at sort of the lower right. Let's go for it. So the first one is this one here. It will get a value of 1. All right. There we go. Now this is, let's quickly go through this row. They all will have values of 1, and this comes from the fact that they indeed are closer to the background. The next pixel will stay at 1, right? And now, what about this guy?
This guy is equal.
Now it's actually square root of 2. Because if we look at this, wait a minute, there's a slight mistake here, damn it. Anyway, it will become a square root of 2. I don't know whether I made a mistake there with this here. But you get the picture anyway. The next one will stay at 2, and actually we're done. So this is it. This is it. The mask is different here. I made a mistake with the mask.
If we are actually looking down right, then
exactly. The mask is wrong. I should have. It's still from the connected component analysis. But anyway, so in the second pass we need a different mask than is suggested here. You can easily, I'll correct this on the slides, but you can easily correct it at home. So this is how we compute the chamfer distance. Right? We have one pass and the second pass, and in the second pass we correct the mistakes made in the first one. There you go, this is it. And yeah, you know, I'm writing it as 1.4, could have written square root of 2, let's say the same number. Yeah, this is it. This is how it can be done in Python. We read an image, we turn it into a binary image, we compute an initialized version of the distance image, set A and B, determine the size of the image, and then we have these two passes here. For loops actually has the same. Here, this is. Okay, so yeah, this is obviously different than what we had on the previous slides, because this one works because I used it to compute. Now, where was it? Damn it! Should not have made this one. And now back again. Horrible. So, yeah, Python, right? For loops have to be avoided if possible. Actually, here it can't be done. There's no way of how to sort of vectorize this. But again, SciPy comes to our rescue. There is, in the NV image, is a submodule called morphology, and that has a function called distance transform CDT. Don't know what CDT stands for, but this does exactly what we discussed. So in the end, if you were to do this in Python, it is just 2 lines of code where I have sort of reading the image divided by 255, 1 minus, this is already turning the image that is being read into a true binary image, and then this computes the Chamfer transform. So yeah, when I began teaching this course and when I began looking into the use of Python for image analysis, this thing did actually not exist, this module. Now it is there, and it tremendously simplifies everything. But again, my message is, of course you can call these functions, right? But you should really know what they are doing. So before you use something, it's always a good idea to actually know what is it that I'm doing here. What is under the hood here? Is this actually something I should use, or is there something which would argue against using this in whatever context I'm currently interested in? Particular note the crazy parameter taxicab here. It's a certain distance measure. Yeah. This is the one closest to the one we have been using here with square root of 2 and 1. Actually, this function does not allow to compute the Chamfer transforms where A would be square root of 2. Is not possible here. Don't know why. It's the one that comes closest. So, but yeah, that's that. But it may be interesting for the exam. I'm just saying. So then let's move on to likely the most interesting idea we are going to study today, the idea of Hough transforms. And the problem that we are interested in right now is the question: if we can, given an image, identify parametric geometric figures such as, for instance, lines, circles, curves, stuff like that. Stuff which, using pen and paper, could be described with an equation. Right? Can we identify structures in an image where you would say this is a line with a certain slope and a certain offset, or this is a circle with a certain radius and center point? We can easily write down equations that describe lines and circles. Is there a way for us to find objects in an image that meet certain mathematical equations? And the typical setting for this problem is, again, we are given an image and we compute an edge map, and that gives us a set of foreground and background pixels. And in this edge map, we look for the presence of such structures. So for instance, the question could be, this is the image, this is the edge map. Are there lines in here? Are there? And we see them, right? But the computer has no understanding of what a line is. This is just a collection of pixels, which, as it so happens, are arranged in a pattern that we as human beings would call linear pattern. Linear structures. There are lines there. But so far, given the representation we have computed from here to here, it is just a collection of pixels. No lines yet. This is, I mean, we see them, but we have not represented them in our code. Can we do that? Now, the idea when it comes to lines, and we'll just go through the Hough transform for lines because this is the most traditional venerable case, but again, it works for circles and ellipses and anything basically else. But let's just study lines. The idea is to think about what it means to be a line. Right? And from, I don't know, high school or elementary school, I really don't know, but let's say high school, we know that a line, at least in 2D, can be expressed using this equation where we sort of see the height of a point on the line as a function of sort of horizontal coordinate x, and the line is characterized by two parameters called slope and intersect, where intersect is just sort of the offset of the line with respect to the y equals 0 axis, and the slope is of course sort of the ratio of like what is the ratio between height traveled and width traveled if we walk some distance on this line. Right? So this is slope and intersect, and there's really not much for me to say about this. This is well-known material. What is not so well known, however, is the following. If we think about what we just did when we said, well, a line equation. And you know, we are interested in lines in an image, so therefore I shall call this image space. So the xy representation of a line is the image space representation of the line in terms of pixel coordinates. I said it, well, y is a function of x, so these things are variables, and m and b are given. They are parameters. So apparently a line equation has two variables and two parameters. And here's the crazy thing. We can solve this equation for b, can't we? Let's do this. We could, looking at this, say, well, if this is the case, then b is minus mx plus y. Let me just put on the other side. But this now seems to be something where b and m are the variables, and x and y are the parameters. It's a form of duality here. Right? This we shall call the Huff space. Now, in the image space, we have this line, y equals m1 x plus b1. I'm using subscripts here to indicate that these are fixed parameters. Now this m1 and b1 in a space bm is just a point. Okay? Can you already imagine where this is heading?
Number of votes by each line into an accumulated.
Yeah, not quite yet. We'll first have to think about what this duality really means.
I think here in the Huff space, what we are saying, this is the space of all possible lines in the 2D.
Yeah.
Parameterized by some.
That's true. Parameters by some line parameters, yeah. Yeah, that's true. Every point there would be a line here. This is what this says. What if I were to draw a line here? Then what would that be in the other space? This is what mathematicians and physicists call duality. In the image space, a line in the image space corresponds to a point in the Huff space. This is very easy for us to see. A line in the Huff space corresponds to a point in the image space. Right? Because a line, something defined over two variables, b and m, with respect to two parameters. This is exactly what we worked out for the image space. Well, now let's do it for the Huff space. So we have a line here in two variables b and m and two parameters x1 and y1. There are the two parameters. So a line in this space is a point there, and the line in this space is a point here. This is actually, if you have never seen this, a really frequent I don't know really, but a frequent phenomenon in mathematics. If you're familiar, for instance, with projective geometry, you know that lines are points and points are lines. Lines are points in some space, and lines in some space are points in the other space. Here we see that with respect to the parameters of line equations. All right. Yeah, this is, if we think about it, it's very interesting, right? And one wants to think, what could this mean? Now, our problem, however, is the following. We want to determine lines in an image. And all we are given is a couple of points. And instead of x1, y1, x2, y2, I just call it p and q to reduce clutter. Right? So this is the image we are given. The line through these 2 points I call L, but it is not there yet. I'm just using it here in this example. This is our image, and we are given a couple of pixels, and we want to identify lines. Now, so we have given 2 points in the image space, 2 pixels, but I just call them P and Q here. And they, of course, define a line I call L. Now, in the Huff space, we just worked out that points are lines. So the point P in image space is a line P in Huff space, and the point Q in image space is a line Q in Huff space. But the line L in image space is a point L in Huff space. This is funny, because whereas in image space 2 points define a line, in Huff space 2 lines define a point. This is duality. It happens quite frequently in mathematics. And this is just sort of a summary of what I just said. Think of it like this: pixels xy that lie on a line in an image, and the line is parameterized like this, correspond to lines in a Huff space which pass through a point. And the point through which these lines in Huff space pass is actually the point that parameterizes the line. And so therefore here is the general idea for the Huff transform. We are given this edge map, say, a collection of pixels, foreground pixels, and we iterate over those. And for each pixel, we compute a line in Huff space, and that will lead to a lot of lines in Huff space. And then we just look, is there some intersections? And these intersections in the Huff space, each of them we find defines 2 parameters for a line in the image space. This is what we do. The problem is, like mathematically this is perfect. Right? Practice is a bit ugly because the images are discrete. And so we are not guaranteed that there will be actually intersections in this Huff space. If we know the image is discrete, and if we do computation with the computer, the Huff space has to be discrete as well. We are not guaranteed that there are intersections. So what we have to do is, we have to discretize it and be a bit general, and we'll see how that goes in a second. There is another critical problem. If a line is perpendicular, the slope is infinite. It's very bad if we want to sort of compute a Huff space. Like, that cannot be done on a computer. Infinite does not exist. It's just not possible.
Mathematically, no solution.
Yeah, mathematically, you know, this actually is a bad thing, but there is a solution. Pardon? Excellent, excellent, very nice, very nice. Here is the solution. We don't have to use M and B. Right? We can think of the line as having a distance, not an offset, a distance to the origin, and this sort of line here has an angle, and these 2 parameters perfectly define the line. Right? And so therefore, instead of using M and B, we rewrite all of this, and I'm not going, this is, you know, kindergarten stuff, like this gives us that. Right? We can actually express the line equation in terms of r and theta, r being the distance of the line to the origin, theta being the the angle. So yeah, that can be done, and therefore instead of using a MB half space for all of that, we now use an R theta half space, but it's the same thing. The critical difference is that what was a line in the half space so far now becomes a sine wave. All right, but I will not discuss this, and we will see them in a second. But can you imagine? Right, I said, okay, a point in image space corresponds to a line in half space. Now, if we represent the lines in image space like this, a point in image space actually corresponds to a sine wave in half space. But that's just a minor difference. We can still compute lots of these sine waves and look for intersections. Here is the algorithm, and I know that I am really vague. This is just pseudocode, because there are certain intricacies and tricks and implementation details that are important for this to work. But then again, this is not a coding lecture, right? So I just give you the pseudocode and hand wave the nasty details away, which you will come across if you ever have to implement it for yourself. However, of course, I have code that does this, and it's not rocket science, right? But I was thinking, I thought, you know, it's not worth to discuss it from the form of actual code. So here we go. We first create our half space. That is, we decide for sort of what is the maximum R we are talking about, what's the minimum R, and this gives us an interval which we chop into bins. I'd say M bins. Also decide for maximum and minimum theta, and I'm not discussing how we do this. This is one of these details. Let's not look under that rock. We have an interval of theta values which we discretize. And then we initialize our half space. It's also called an accumulator. It's just a matrix of the size of the number of intervals we have chosen for R times the number of intervals we have chosen for theta. And we initialize this matrix of dimension n by n, mn, so that at the beginning every entry of this matrix is 0. Then we iterate over all the foreground pixels in the image, say the edge pixels we have in our edge map. And then for every foreground pixel, we iterate over every theta value. We have to create the line or the sine wave in half space. It's not just a point we have to create, but a whole sine wave or line. Right? So we actually have to do this. We have to go over all theta values and then compute corresponding R values given x and y and the currently examined theta values. So this creates actually not just one point in this accumulator, but a whole set of points. And we store them there. Once we are done, we go through this matrix, R and theta, and look at, I don't know, entries where there is more than 5 or 50 or like some threshold counts in that bin of this matrix. And for every entry in here, we would say, okay, that defines a line. Here is an example. This is too bad. There are, I don't know, can you see, there's something bright here, can you see it? So there are lots of sine waves, and wherever it is bright, many of these sine waves intersect. So this is the image, this is the edge map, this is matrix A. We can't see anything here, you have to look at the slides. I'll upload, and then I just thresholded this, and for every parameter R and theta I got from this accumulator, I plotted a line in this image, and this is what you get. It has found lines. Unfortunately, it has found many lines for where there is just one line. Why is that? Any idea why here there is a bundle of, I don't know, 5 whatever lines where you would say this is just sort of one line?
Because of the edges?
Yeah.
Edge or like, because there is no exact sharp edge. For example, there is white and black, but
Yeah, exactly. Actually here these are either black or white, but this is a couple of pixels close to this. It's not, this edge here is not just one pixel thin.
Yeah, exactly.
Yeah, so there you see one of the problems. If you do this, this works really best if you thin out these images such that all the edges in here are really just one pixel thick. How could we do that? Something we studied in the last semester? Morphology?
Yeah,
Erosion, exactly. So it is a good idea to erode these images. I didn't do it. I was too lazy. And even if I had done it, it's still, so again, is this a great idea? This is a perfect idea. This is again one of sort of the triumphs of human intelligence. Like, you know, how to come up with this. When Huff invented it, he immediately patented it as well. The patent is free now, it's like so long ago. This is great. This is really great. But look at it. How to choose all these things. Nobody knows. Seriously, nobody knows. It's so sad, right? It's so sad because again, you may now be tempted to think, yeah, now I know how to detect lines. And of course you know how to detect lines. And then you sit down and, you know, write a code that does this, and then what you get is this. And of course I was tremendously disappointed, but I really thought it worth my time to play around with these parameters until I didn't get fewer lines, sort of crisper lines, right? You have to be aware of this. This is how we find lines. This is how we find lines, right? But again, the details, as always, depend on your particular situation. Right? In particular, if you're dealing with a larger image or a smaller image, you have the sort of the same amount of M&M, but in the larger image, there will be more foreground pixels. So it is very likely that in the larger image, your accumulator will have larger values than in the smaller image. So therefore, how to choose this? Right? One idea is to normalize the accumulator and see, but these are things you have to keep in mind. Okay. So this is how we detect lines, but there's at least 5 parameters in there that can make your life a mess in practice. Theory works beautifully though. This is how we do it. Just a couple of remarks. Again, this accumulator may suffer from noise. Maybe there's some pixels being set that shouldn't be set, whatever. So you may think of smoothing it. Introduces yet another parameter. I didn't do it for the results I've shown you, and actually it didn't make a difference. I actually tried this one. Didn't make a difference. I said earlier that this, the general idea is to look for mathematical objects like lines, circles, ellipses, and so on and so forth. Here is another mathematical object. It's a circle equation, right? X and Y are the pixel coordinates in the image, and this is obviously something we can write down using pen and paper. It involves 3 parameters. So here there would be a duality between the image space and a 3-dimensional half space. Right? Because the object we are after here right now requires 3 parameters. But apart from that, everything is the same. Everything is the same. Is of course, more for loops in the code, right? Because so far we looked at 2-dimensional half spaces, now it would be 3-dimensional, one more for loop. And so therefore, this algorithm is actually really slow. It's really slow, and that is because for every foreground pixel, we have to create all possible lines in half space. And then we have to look at if they intersect. Right? So that is to say, for the problem of line detection, for every pixel, we actually have to compute every line, which, you know, it's tedious. And for a circle, we actually have to create, every triple of parameters, which it becomes slower the more parameters the object we are interested in has. it works for everything. You can, like any mathematical equation in x and y, can be turned into Huff transform object finding. But the more parameters there are, the slower this algorithm will be. With respect to lines, because it's such an important problem, people have thought a lot about what to do. There are very fancy improvements involving gradient direction information, so you don't actually have to create every line, but probably only the lines perpendicular to the gradient at the point. Very good idea if you think of it. This basically is in just one line of words to say we do not have to create every possible line for every x and y, but just those lines that are perpendicular to x and y in the image. Or you may think of crazy sampling schemes, right? Don't do it for every point in the foreground, just for some of them, but then again how to choose those, so careful with this. But there are ways of speeding this up, and it is not worth our time to look into that in detail. What is most interesting about all of this, at least from my point of view, but that is again personal taste, that there is a very clear-cut probabilistic interpretation of what this algorithm does. It can be indeed expressed in terms of conditional probabilities, right? And can be thought of as a maximum likelihood approach, but that would take us too far afield from what our interest is in this lecture. So I'll not discuss that, but the algorithm actually makes a lot of sense from the point of view of probability theory. And that is all I have got for today. What we now learned is how to determine disjoint regions, like answering the question, how many regions are there? Up until today, we were sort of able to find regions, but they still were characterized in terms of, oh yeah, they all have this feature, but can happen here and there. But now we actually know that this is a different region than this one, using the idea of, say, connected component analysis, which can be computed very quickly using two-pass algorithm. We looked into the Chamfer distance transform, which is of interest in the area of template matching. This is actually where it's most interested, of most interest. Template matching when it comes to very regular objects that can be basically characterized in terms of geometric shapes, such as squares, circles, triangles, stuff like that. With Chamfer matching, we would not suffer from variations in scale or rotation as much as we would if we were to do it directly in the image or in the edge map. It might be of interest for the example, I'll just say. And then we looked into the notion of Huff transforms. And the one we studied in detail was the original one, the idea by Huff of how to find lines in an image. We saw that there is a duality going on with respect to the parameters of mathematical equations. This is a very general phenomenon. So how that can be turned into computer code, well not really, but into an algorithm for line detection. And I mentioned, and I just mentioned it, that this will work with basically any kind of mathematically expressible object. And that is all I have got for today. Do you have any questions? Well, if not, then see you next week. Thank you.